4.7, number 320. 320 says you have 800 feet of fencing to make a pin. And that pin sits along a river. The river is one of its sides. I'm paraphrasing the question. We want to find the dimension of the rectangular pin that maximizes area. Find the dimensions of pin that maximize area of the pin. This is really just one step down in terms of dimensionality from the example I did in the beginning, because there we're working with a box and we're talking about its surface area being fixed and the volume being maximized. This is very similar, just one dimension down. This is the surrounding of the pin is fixed at 800 feet, but we're going to maximize the interior, right? Just like the volume is the interior of a surface, the normal area here is the interior of a certain perimeter, right? So I'm going to draw a picture. Again, I find it helpful in a lot of these problems to draw pictures. So we have a river of sorts. Okay, there's a river, and there's a pin with one side. Right, there's my pin. One side is the river. So what to label? We have these two sides being the same because it says it's a rectangular pin, I think. It actually does not say it's a oh yeah, it is, yeah. It's a rectangular pin. And this does not have to be the same as these two. These two have to be the same because it's rectangular, but this one does not, so therefore we have introduced two variables only again. I would not say x, y, z. That would cause too many variables to be in the problem, way more than necessary. But the fact that this piece is missing means that unlike the previous example where the box became a cube to maximize the interior, we would anticipate in this problem for this rectangle to become a square to maximize the interior, and that would be true in general. But because one of the sides is missing, this will actually not end up being a square that maximizes the area. It will be a rectangle which is not a square. But it's only because one of the sides is missing. All right, so we know that the perimeter rectangle is 2x plus 2y, but one of the sides is missing, so this one's only 2x plus y. Okay? The perimeter is really just what are we contributing fence to? We're only contributing fence to 3 of the sides out of 4 because the other one is blocked off by the river. So area, though, that's our objective function. It still is x times y, right? This interior is still x by y. Nothing's going to change that. So again, we have an objective function and a constraint. This problem will probably seem a lot lighter than the example I did. Again, because the dimensionality is one less than before. And the perimeter is our constraint. What's the constraint? This has to be 800. Right? All right, so we've got the constraint and we've got the objective. So now we're going to solve the constraint for one of the two variables. I'm going to pick y again. In this type of problem, it really doesn't matter. It's not, I guess it's a little bit easier. I just subtract 2x. I don't have to divide off by anything to solve for the variable y, or if I solve for the variable x, I've got to divide by 2 eventually. So maybe it is just sounder to go ahead and solve for y. So we take 2x plus y equals 800 and solve for y. 800 minus 2x, and we'll plug that into the objective function. So we have a, which again is 2 variable at first. I'm just writing it this way just to keep in mind why it's such a goal to make this substitution is because we don't know how to properly work with multivariate functions with the calculus we know so far. So we've got to render it into single variable. That would be x times 800 minus 2x. All right, again, I could do a product rule on this. I'm going to take the derivative set equals 0 to use the first derivative test, but I think it's better with these small polynomials just to go ahead and multiply through. Now, having said that, I'm going to go ahead and take out a factor of 2, though, which is really unnecessary to be inside here. So 2, and then I would have 400 times the x minus x squared. Okay? So I factored off the 2, but introduced the x to the inside.